One small step. We've all heard the story of humanity's first steps on the moon. But what about our last steps? In December 1972, two astronauts climbed into a small metal capsule and prepared to return to Earth. The Apollo 17 crew included the first scientists to set foot on the moon, and the astronauts spent more than 3 days exploring. They conducted more experiments and examined more of the surface than any previous mission. This concluded the Apollo program. More than 10 years' work by 500,000 men and women. In a competition between the United States and the Soviet Union, known as the space race, humanity proved that we could walk on the moon. When the Apollo 17 astronauts blasted off, most people thought we would return soon, but we didn't. Apollo hardware sits abandoned on the lunar surface for more than 40 years now, relics of another time. For many of us, the space race seems like ancient history. Some people miss the glory days of Apollo's explorations. Others think the missions never even happened. Children who once played at being astronauts have grown up, had children and even grandchildren of their own. Now, the next generation of explorers will make the journey.
So we are privileged to have with us tonight one of those two astronauts who last stepped on the surface of the moon, Dr. Harrison Jack Schmitt. Who is going to be talking to us not only about Apollo 17, but also about the future of where we go in terms of exploration with a whole new generation of infrastructure. I want to welcome you all first to the Fiske Planetarium. I'm Jack Burns. I'm a professor of astrophysics and planetary science here at CU, and it's my great honor and privilege to welcome back to Boulder an old friend and colleague, as I mentioned, Harrison Jack Schmitt. Dr. Schmitt received his PhD in geology from Harvard University, and as you saw in just a little clip here a moment ago, he's the only scientist, the only working scientist, a field geologist, to have gone to the moon. We hope that's going to change quite a bit in the future. We have many more scientists who will be going to the moon and to explore and do some science. Dr. Schmitt was part of a crew of astronauts selected in the mid-60s, specifically for the Apollo program. After he returned from that mission in 1972, he ran for political office and was elected to the United States Senate from New Mexico, just to the south. Served one term from 1979 to January of 1983, and that's when I first met Dr. Schmitt. I was on the faculty at the University of New Mexico at the time, and Dr. Schmitt was my senator. So we first met then, and after he returned to Albuquerque, we found ways to work together on a number of projects over the years. He's remained very active in and around NASA and the space program. He and I served together on the NASA Advisory Council back about 10 years or so ago, working in those days on some plans for return to the moon. And today, he remains very engaged, among other things, a member of what's called the Users Advisory Group associated with the National Space Council. So without further ado, let me have you all welcome Dr. Jack Schmitt.
Thanks, Jack. Thank you. Very kind. Is everybody fully dark adapted? Huh? You think? Because I have some small gray images of the moon here in my hand. And I would like, particularly if there's some young people in the audience, to raise their hand and I'll try to get it to you. There's one over there. How about over here? There you go. Good catch. Oh, here we got one there. Oh, somebody got it for you. How about here? And one more. Oh, they're back there. There you go. Those are very soft. You know, when I first thought of throwing some moon balls out, the ones I got were hard. And sometimes young people will watch those things coming towards them and not move. So I got softer ones. What we're going to do tonight, through the kindness of the planetarium and Jack Burns, is take a very quick trip to the moon, talk about some of the things that went on there, and then maybe think about the future some, and take a few questions. If that's okay with you all, we'll proceed. If I could have the first slide, please. How about the second slide? I knew some of you were very concerned about this, and if you think about it, you'll get it. Spacebar, right? Next slide. This picture is, I think, the only picture of Neil Armstrong on the moon. And I like to show it just because Neil did such a fantastic job, not only in piloting the Eagle to a landing and meeting President Kennedy's challenge to my generation, but he also was filling up the rock box with lunar samples. And since I'm a geologist and a lunar geologist in particular, that was very important. And Neil told me that when he looked into that box after collecting a really fantastic suite of rocks, he said it looked sort of empty. And so he filled it up with moon dirt, lunar soil, regolith we call it. That has turned out to be one of the most important samples ever collected on the moon because it is the basis for our understanding of the resources that are available there, not only for lunar settlements that some of you young people may participate in, but also for what is going to be necessary to go to Mars. We're talking about water and hydrogen and oxygen and the like. So Neil did us a great service, as he did humanity in what he did for the Apollo program. But let's do a little history. First, please. Next, please. The groundwork actually for Apollo was laid by President Eisenhower. Most people probably don't realize that. But NASA was formed in his administration and the bipartisan support of Mike McCormick in the House and Lyndon Johnson in the Senate. He ordered the Army to transfer the von Braun Group and others to NASA, as well as the laboratories of the old NASA Advisory Council on Aeronautics, and also the JPL laboratory. So all of that took place. The basic groundwork for NASA was laid there. He also, in January of 1960, ordered his administrator, T. Keith Glennon, administrator of NASA, to begin the development of the super booster, which became the Saturn V. And if there's one basic enabling technology for Apollo, it was the Saturn V. Next. I hope you all realize that Apollo was not a scientific endeavor. It became one due to the foresight of many, but it was part of the United States response to the Cold War. Next. Kennedy proposed this landing and or this mission in 1961, May of 1961, next. And it was basically to counter the advances that the Soviet Union had demonstrated in human spaceflight. Next. Next. John Glenn, as many of the advanced folks in the audience will remember, orbited the Earth in 1962. Next. Apollo 8 orbited the Earth in December of 1968, almost 50 years ago. Remember now, we've just begun the 50-year sequence of anniversaries of the Apollo missions. The first, actually, most important mission, Apollo 7, took place came back to Earth just about 10 days ago. Next. Neil successfully landed, and many people think that ended the moon race, or that Apollo 8 ended the moon race. Actually, the Soviet emigres who were involved in the Soviet space program at the time will tell you that the first successful launch of a Saturn V ended the moon race. That's when the Soviet leadership realized that they had lost that particular race. Next. There were 5 additional Apollo missions that landed on the moon. Next. Apollo 13, as you may recall, and if you haven't seen the movie Apollo 13, you should. It's one of the best movies, I think, ever made about space. That explosion resulted in the rescue of the mission, a very successful rescue conducted primarily by the Mission Control Center in Houston. Next. The last 3 Apollo missions all went to different areas, scientifically important areas of the moon. They each one had 3 full days on the moon, 3 full excursions, and through all the missions, we collected 850 pounds of moon rocks and soil that have been very important and continue to be the gift that keeps on giving. There's a very, very active lunar science analysis community. And with the advance of new analytical technologies in chemistry and isotopic analysis, these samples continue to give us new information about the moon. And I see no reason why that will ever stop. Next. From all of that, if you ask what is the most fundamental and most important scientific finding, and there were many certainly about the moon itself, probably the greatest was that we now understand, as a result of the Apollo science, what the early history of the inner solar system was like, and in particular, the early history of the Earth, a history that's obscure to us because of the very dynamic geological processes that still take place within and on this planet. And that is a history, an extraordinary violent history, based on what we know about the moon, a time in which life was beginning to get organized on this planet. So there are not only fundamental biological issues involved here, there certainly are also philosophical issues as well. Next. Now, in July of 1969, we launched the Apollo 11 mission. Next. By the way, that was only a little over 60 years since the Wright brothers flew the first airplane. Not very long in human terms, even. Now, I like to quote von Braun here because all of us should remember this. I have learned to use the word impossible with the greatest caution. Wernher von Braun certainly lived that by experience, and the reason I show this old, probably Model A, right? We got an expert in the audience? It looks like a Model A. That was Robert Goddard's crawler, if you will, that took his rocket out to a launch site near Roswell, New Mexico, and its size compared to the Saturn V is compared on the right-hand slide. Next slide. Now, I just show you this picture, I like it. I like to see Mike Collins, Neil Armstrong, Buzz Aldrin, very serious before their mission, probably watching for the indication of what we call the acquisition of signal from the Apollo 8 mission as they came from behind the moon. That happened exactly when expected, but it was certainly something that got everybody's attention. Ken Mattingly and I are there equally concerned that this would happen at the right time. Next slide. We had a lot of different kinds of training. This one is sort of fun. We did survival training in Panama and other places. And why did we do survival training? Well, in the early days of Apollo, we weren't absolutely sure the guidance system would actually drop us in the right place in the Pacific. And in this case, that we might come down in some jungle areas. We even did desert survival. We certainly did a lot of water survival training. Here you see Ed Mitchell, yours truly, and Ron Evans. Ron Evans and I did not know it at the time, but we flew together on Apollo 17. More about him in a moment. Next. If I ever needed another career, I could become a bandit as a result of this. You might be interested to know that NASA had a machete in our survival kit, which broke the first time I tried to use it. And this is one I bought from our guide that periodically appeared. He obviously had a supply of these and knew the NASA machete was going to break, so he sold us this for $5. Next slide. Well, this is really all about Apollo in this picture in many ways. The Saturn V, 6.8 million pounds fully fueled. The 5 big F1 engines in the first stage developed 7.5 million pounds of thrust. You'll see a picture of that in a moment. The vehicle assembly building there on the right, you get a feel for scale, I think, by looking at the very large fire engine there just near the open bay. It was at the time the largest enclosed space in the world. That subsequently has been exceeded by first, I think, the Mall of America in Minneapolis. And then now I believe there's a 787 manufacturing plant in South Carolina that has a greater enclosed space. But this still was spectacular and is being utilized more and more, not only by NASA for the Space Launch System, but also by SpaceX, and I believe it's even Jeff Bezos plans to use it at some time in the future. Next slide. That's the Saturn V launch of Apollo 17. If you look carefully there on the left-hand side of the rocket are some bright spots coming off the side of the rocket. Those are big flakes of frost. We had to sit on the launch pad in that humid Florida atmosphere for about 2 hours and 40 minutes. That meant that we had a lot of frost condensed on the side of these very cold liquid oxygen and liquid hydrogen tanks. And fortunately, there's a very heavy vibration during launch. If any have ever driven down railroad tracks, I don't recommend this, but driven down the ties of railroad tracks at about 30 miles an hour, you'll get an idea of what that vibration was like. And indeed, it was so high, I could not read the gauges in the cockpit. So in spite of all my training, that particular part of the training didn't make much sense because I couldn't read the gauges during launch. Had that engine ever shut off, I'm sure I could have read the gauges very well. Next, the two spacecraft, are the Command and Service Module in the upper right and the Lunar Module Challenger in the lower left, were all up in the upper part of that of the rocket, just above the third stage. These spacecraft were extremely serviceable, very robust, as was the rocket itself. And I guess the most unfortunate outcome of Apollo is that there was an outcome. We stopped. And because we had a system that worked very well in deep space, and had the manufacturing management been set up to continue the production of these systems, they still could be in use today, upgraded, obviously, and with new technologies and new software. Next slide. I don't show you this to show you how much time has changed my appearance, but just to give you an idea of the other spacecraft, namely the spacesuit. When we had the backpack on and were inside and fully functional, it was indeed a spacecraft. It had life support, it had cooling water, and everything you needed to to operate on the lunar surface for about 8 hours or even a little bit more if you had to. Next. Oh, can we go back one? Yeah. I just want to point out, you wonder why the various valves there or entry points are colored. Blue means something's going into the suit. Communications, water, oxygen, you name it. And the red means something was coming out, mainly oxygen that was then going to be recycled and the carbon dioxide removed from it. Next, please. That's for the nerds in the audience that really were. Gene Cernan and I trained, as all the astronauts did, in a very extensive program of geological familiarization on issues, geological issues that might have some relevance to our landing site. We had all the equipment. The only thing we didn't use on these training trips, which happened about a week a month, were the spacesuits. But everything else we got familiar with, the cameras, the Hasselblad cameras, everything was outfitted pretty much as we would expect to see it on the moon. And it turned out a very, very efficient and motivating way by which we all learned, pilots in particular, not only how to use the equipment, but we learned something on real geological problems. And that was the training program instituted initially for the Apollo 13 crew, but all the missions were exposed to it. Next slide. I like to show you this picture because sometimes when I show it, people say, well, that's ice. No, those are clouds. Just clouds over the South Atlantic. We were finally in lunar orbit. And I want you to remember that band of blue that you see in the upper left. That is, of course, our atmosphere. That's what keeps us going down here. And I'll bring that up again when we get to the moon. Next slide. This Blue Marble photograph, which NASA tells me is still the most requested photograph in the NASA archives, is one I took from about 34,000 miles away in order to document weather observations I was trying to make and did make while on the way to the moon. About 3.5 days, I filled page after page of audio transcript with observations of these southern hemisphere weather patterns, which you can see are significantly more symmetrical than we're used to seeing in the northern hemisphere. And in fact, there's the intertropical convergence zone across the equator is quite visible. That's where most of our terrestrial thunderstorms occur. And then in the upper right, there you can see there's a typhoon going ashore on the subcontinent of India. It really was a fascinating 3.5 days for an amateur meteorologist like myself. Next slide. Now, this gives you an idea of where we landed relative to Apollo 11. We were landing in a deep mountain valley that cut through the ring of other mountains that surround a basin called Serenitatis. That basin's about 750 kilometers in diameter, formed about 3.86 billion years ago. So it was one of the many basins forming in about that period of time. And you just got to remember that during that period of time, not only were these basins forming on the moon, but similar impacts were occurring on Earth. Like I said earlier, an extremely violent time, and one in which life was beginning to take hold here on this planet. Next slide. This is the first view I had of the far side of the moon, and the reason I pointed out that little band of blue on the previous photograph of the South Atlantic is that it's not there around the moon. There's no atmosphere. There's a transient atmosphere, very thin, disappearing all the time, but there's no sensible atmosphere, as you can see in this photograph. But the color there is about right. The light-colored illuminated areas were slightly tannish, and of course the unilluminated areas were deep black. Next slide. The Valley of Taurus Littoral, where we were headed, is this valley you see here from the upper right to the lower center is about 50 kilometers. It's at the narrowest point there, it's only about 7 kilometers wide. That object in the near center is the Command and Service Module America. Ron Evans now is all alone in that vehicle. This picture was taken from the lunar module on the orbit of the moon just prior to us actually starting the descent engine to land in the valley. Ron was doing a very important task, and that is what we call landmark tracking. He was establishing his position in space relative to some craters on the valley floor, the position of which had been determined previously relative to the center of mass of the moon. And of course, when you're orbiting, you're being controlled by the center of mass, largely controlled by the center of mass of the moon. That was very important in order to, because then that knowledge of his position was recomputed on the ground through telemetry and sent back to us, so our position was improved as well in the lunar module. And that meant we could land with a relatively small error margin in the valley of Taurus Littrow. That valley's deeper than the Grand Canyon, by the way. The mountain in the center there, the South Massif, is 2,100 meters high, over 7,000 feet high. So it was really a magnificent place to be, as I hope you'll see more of here in a moment. Next. Now, this is a Lunar Reconnaissance Orbiter image. Lunar Reconnaissance Orbiter is currently in orbit around the moon. It's in a stabilized orbit, but it's still taking photographs of various parts of the moon. It has essentially covered the entire moon, and I believe the early pictures we saw of the moon were actually mosaics produced by the Lunar Reconnaissance Orbiter images. That really was remarkable. Now, what this picture shows is low angle, oblique, low sun angle. It shows the scar of an avalanche. That was an actual avalanche of lunar debris, what we call the regolith, that came off the side of that mountain. But I also show you that plume-like deposit. I also show you, though, because the Challenger is indicated there as that bright spot, right there. That's where we landed. This is a picture taken more recently, obviously, by the Lunar Reconnaissance Orbiter. The reason it's bright is because as the effluents, the gases from the descent engine, hit the surface of the moon as we were landing in close to it, it would winnow away fine material which is darker than the coarse material. And so you ended up brightening the surface, as you see there. Next. The first view, though, I had nearly 50 years ago out of the lunar module was this. Out of the right-hand side, after landing, very typical surface, Mare surface of the moon. Basalt underlies this. It's been pulverized and mixed with other material. This debris in here is about 9 meters deep. It's really a very thick covering in the valley. Or where Neil Armstrong landed, it was about 6 meters deep. So it varies from place to place, but it's always there. The base of the North Massif over here is about 5 kilometers away, 3 miles, maybe a little bit more. And this object is one of 16 small restartable rockets that we had to control the orientation of our spacecraft during flight. The thrust on those rockets was about 50 pounds. The thrust on the F1 engine of the first stage, engines of the first stage of the Saturn V was 1.5 million pounds. And so you see the spectrum of propulsion technology that we harnessed in order to achieve the goal of landing a man on the moon. Next slide. Now, a couple of days later, after working outside the spacecraft, you see this surface has gotten pretty badly stirred up. It has very high bearing strength initially, but as you walk on it, it gets stirred up. It's a lot like damp beach sand. If you've been on the beach where the sand's a little bit damp, you've seen the same process work. It's slightly cohesive, but it does break up. Next slide. This is everything you need in order to live and work on the moon, at least for 3 days, okay? You need a camp. That was the ascent stage. You need a vehicle, that really helps. I mean, if you don't have to walk quite as far, you can go a lot farther, of course, with a vehicle. You need this spacecraft I mentioned earlier, namely the suit, spacesuit. And of course, you need the support of the American taxpayer. Next slide. And in our case, like in several of the other missions, commanders tend to be a little bit careless about where they put their hammer. I use a scoop. The hammer, even though geologists always use a hammer here, the hammer wasn't very effective with this kind of material. But he had it in his right hand, or in his left hand suit pocket down on his calf. And as he walked by the fender, he tore it off. And this is the fix that the Mission Control Center came up with overnight, and we clamped on the fender, and it worked extremely well. And as you might guess, this tape holding that fix together is gray duct tape. We had a nice big roll of it in the spacecraft. Next slide. Wow. Bit of a panorama for you, folks. This was a panorama at Station 5. These back here in the back of the room, if you can turn around, these are all big basalt boulders that have been thrown out of a 600-meter diameter crater, and my light is going along the far rim of that crater. Just as an aside, scientific aside, we've been able to reorient these blocks relative to where they were originally before the impact. And in doing so, we have actually been able to make some measurements of the lunar magnetic field that was present at that time. A colleague of mine at MIT, Dr. Weiss, has been doing that, and we now have not only that there was a magnetic field and what its intensity was, but we know its paleo, or its old orientation as well, and from other measurements we're getting to know just how long did that magnetic field last on the moon. Next, please. Ooh. Here we go. There's yours truly, once again. This is one of our sampling devices. It gives you an idea of the backpack. This is emergency oxygen supply. The camera, the Hasselblad camera that worked extremely well for us on the moon, took all the pictures you're seeing of on the surface. This is what we called our rake sampler. It actually was a sieve. The idea was to get a concentration of larger fragments, centimeter or bigger fragments, because we figured that we would get some exotic fragments coming from other parts of the moon in that collection. And it worked out pretty well most of the time. In this particular case, we got just what was in the local area. But most other places, we got what we wanted. But this was an important sample nonetheless. Next slide. This big boulder actually was visible on the pre-mission photographs. The pre-mission photographs had a resolution of about 15 meters. And so this was just barely visible. So we planned to go there and sample it and study it as best we could. And it actually had rolled down the side of the north wall of the valley, left a boulder track, so we knew exactly where it came from. And there are other boulders that we can identify by these boulder tracks. And so that gives us a way to sample these high mountains without actually having to climb them. And that's very nice. Yours truly there for scale. The lunar module is parked over here underneath that black arrow. This slope here is about 20 degrees slope. Behind the picture, the photographer, the slope is about 26 degrees. And this rock bounced down the mountain. It actually bounced. There's a whole series of craters that constitute that boulder track. And when it hit this change in slope, it broke into 5 pieces and stopped. And that seemed to happen pretty routinely along the base of these massifs. Next slide. Well, it's often said there's no color on the moon. Buzz Aldrin referred to it as magnificent desolation. As a geologist, I have to disagree with Buzz. But this is a deposit of volcanic ash that I discovered. We didn't know it was volcanic ash until we got the samples back because it's so fine. The individual particles that make up this deposit are only 40 microns or less in diameter. They're really small. They're little beads of volcanic glass. This eruption occurred about 4.5 billion years ago, and this is a color representation of it that comes from the hard work of a colleague of mine, Ronald Wells, who is an expert, along with his son, in restoring the color balance in these pictures. The color's not imposed on it, it's just that you pull out the colors that are in the emulsion and were not developed in the original photograph. This is a very important sample relative to understanding the origin of the moon, as well as its potential resources. Next slide. Well, I know you didn't want to see me standing around in my underwear, but I wanted to illustrate that we were having a pretty good time while we were up there, and we did. I enjoyed the whole trip immensely. This is actually what's called our constant wear garment. NASA can't call it underwear. It has to be a constant wear garment. But it was only constantly worn in the spacecraft. Next slide. Excuse me. Well, this, you saw a liftoff from the video. This is a still shot of it. The commander asked why I didn't go outside and get a really good picture of liftoff, and I declined, as you might expect, having other ideas about what I might want to do with my life. But someday, some of you maybe in this room are going to be up there, and you really will get a really good picture of liftoff. This was actually taken, of course, off a television screen. Next slide. Back to the Lunar Reconnaissance Orbiter. It has taken very high resolutions of images of each of the 6 landing sites. This happens to be ours. That's our descent stage. Here, if you look carefully, you'll see the resolution is good enough to actually identify the dual tracks of the rover here as we headed off this way. And this is my very tortuous track going out to try to find a place to deploy the Apollo Lunar Surface Scientific Experiment Package. And that's where that was deployed right there. The lunar rover was parked right over here in order to get the pictures you saw in that video earlier of the liftoff from the moon. And at any rate, this LRO, the Lunar Reconnaissance Orbiter, is just doing a magnificent job of getting us the kind of information we would have loved to have before our mission, but it's something that those of you who go back to the moon will have as a resource. Next slide. Well, rendezvous occurred very quickly. We actually did what's called a direct rendezvous. We did not go into orbit as others had and catch up. We had enough confidence in the guidance system that we just went directly to where Ron Evans was orbiting and hooked up with him. This is the ascent stage. Later was impacted into the moon as additional information for our various seismic experiments. Next slide. Ron is going to star in this picture because he was all alone up there and thought up all sorts of, not only did he have a lot of tasks to do, experimental tasks, but he thought up some of his own. This is a hydrogen bubble in a food pack that he's enabled. Our water was produced by fuel cells, which combine hydrogen and oxygen to form water and to give us electricity, okay? But a little bit of hydrogen always crept over into the water. And we spent a lot of time trying to give the engineers a hard time for not getting all that hydrogen out of our water, because if you ingest it, you know what's going to happen ultimately. It's going to come out somewhere, much to the discomfort of your crewmates. And Ron has done a good job here, and he is using our experimental food of choice, which was salmon salad. Salmon, it was good. It wasn't spoiled or anything. It just doesn't travel well. I think you know that salmon doesn't. And so if you go into museums and planetaria or anything like that that show you astronaut food and they show you some salmon salad, remember it's what we brought back, not what we actually used. It always reappeared in our menu. It was always there, but most of it came back. Next slide. Well, we re-entered the atmosphere at 25,000 miles an hour, about the speed that we left. The parachutes came out at 10,000 feet. In order to get from entry to that point, though, we had pulled about 7 Gs to make sure we were captured, then held 4 Gs as the computer literally flew the spacecraft to where it had been told that the carrier was waiting. The carrier actually was waiting a little bit farther away, about 5 nautical miles, and the Navy just didn't want a carrier landing of one of these spacecraft. And supposedly it would have survived it. I don't know. That's what they kept telling us anyway. But anyway, next slide, we splashed down in the Pacific, not too far from the island of Samoa. And next slide, we had pick up from the ASW carrier Ticonderoga. And now, if you want to know who's who, this almost certainly is me, because I have black hair at that time. This is probably certain, if you could see it in high resolution, you would see that it's slightly gray. He was getting gray, I think, on his 10th birthday. And this bald head here is Ron Evans. And I think he was bald on his 10th birthday. Yeah, you pretty much can see it all. But anyway, the Navy divers, they were called UDT teams in those days. They were SEAL teams, but underwater demolition teams, were in the water immediately. They had this collar around us, and everything was hunky-dory, except that's not a very good boat. Your main desire is to get out of there. It really is. Even if you didn't get bothered in space with sensory conflict, you're going to get bothered if you're sitting in a hot capsule on the Pacific Ocean. Next slide. Well, ladies and gentlemen, I'm going to end there, and just want to demonstrate to you how much we gained from the Apollo program. It was obviously a fixture of the Cold War of the 1950s and 60s and 70s, but it was very, very important in the development of technology and development of science, and in the pride and of the American people. And maybe most of all, it's benefiting what's going on down here even today. Next slide. I think we have some video at this point. Oh, I wanted to show you this too. Everyone took a picture of Earthrise. I think this is the best one, of course. It sort of is what maybe some of these young people in the audience will see as they head on to Mars. Next. That it? Go into the video. This is a test launch on a Delta IV Heavy of the Orion space capsule. That is the current replacement, if you will, for the Apollo capsule that you saw in those previous pictures.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
You think that's something, you should have been near a Saturn V. And by near, I mean even 3.5 miles away. There we go. This is a NASA simulation of the Space Launch System as the current version of that. Now, it's using solid rocket boosters instead of the liquid fuel boosters that we had on the Saturn V, but it's a comparable area of technology. They're the boosters that, like we're using on the space shuttle, being jettisoned, and then the upper stage will fire to get the, that was the escape tower going off, by the way. Now it's headed to orbit with the upper stage. Solar cells are being deployed. And it's hopefully one of these days we'll head off towards the moon out of lunar orbit with a much bigger stage. And will look something like the following. Back to the moon. It'll have a crew of 4 ordinarily, as I recall, but has the capability to actually fly with 6 or 8, I think. In 6 in a rescue mode? Recognize the tune? So who knows? We, if we can get our focus right, and we now have a charter from the administration to move forward back to the moon and onto Mars, and if we do our job right, those of us who are involved in making these things happen, well then some of the young people here tonight may actually begin the settlement of the moon, the use of its resources, and preparation and prepare to go on to Mars. Thank you very much, ladies and gentlemen. There.
Dr. Schmidt's going to take some questions, and I'll try to serve as a bit of an MC, get over to you to listen to your questions, and boom, there you go. You flew right through the moon. So,
excuse me.
Just we'll take a moment.
Line up your questions, Jack.
What do you believe is the biggest technical or bureaucratic obstacle in returning to deep space?
Well, the biggest bureaucratic obstacle is getting a focus within the NASA, National Aeronautics and Space Administration to do just that. As I think I indicated, I think the charter is there. The direction is there. It's just a question of developing the focus necessary to make it happen. The biggest technical one, I think, is getting a Saturn V capable rocket ready to go, whether that's the SLS and its derivatives or whether it's one of the commercial rockets. We're a long way from having that capability. To give you some idea of what that is, the Saturn V that took us to the moon put 44 metric tons into a trajectory to the moon. We're a long way from anything close to that. We may be, with the current Saturn V, our SLS, Space Launch System, that's being prepared for a launch hopefully soon, it would only have the capability to put about 2 metric tons on the trajectory of the moon. So that has to evolve a great deal before we're close to what it takes to really start to do new things on the moon. Establish settlements and bases and things like that.
Okay, well, I'm going to try to wander over this way. We got another question. So let me just try to weave my way in here.
While he's going, I'll just say that also there's not been any significant work in since the Bush administration on a lunar lander, and that has not started. It needs to start right away. That's, I think, the key geopolitical issue that we have to have. We have to get back to the surface of the moon.
First, let me thank you for your courage that you showed early in your life going to the moon. My question is commercialization opportunities for use of the moon and the resources that you've referred to?
Well, I would, if I were emperor, I would have the private sector do the resource development on the moon. I don't think government does resource development very well. And those resources are significant. For use in space, as I indicated, I think earlier, you have water, which can be converted into propulsion, hydrogen and oxygen propulsion fuels. You have carbon. And all of this just is loose in the regolith, or in the debris layer covering the moon, and it comes from the solar wind, the sun. Carbon is there, and that in turn can become methane, which also can be a fuel. Hydrogen and oxygen can also fuel fuel cells. There are just a whole bunch of uses of those resources. There's also a great deal of helium, which is an important pressurization gas for various propulsion systems, and a light isotope of helium, helium-3, even though not there in great abundance, has tremendous energy potential for use here on Earth. As a fusion fuel. So again, the resource potential of the moon is significant, provided there is a customer in space. We know there would be a customer here for energy, and the question is it competitive cost-wise to bring helium-3 back? And that's a trade study that just needs to be done. I think it is, based on my preliminary work, but that needs to be done in a much more rigorous way than I've done it.
Jack, another question over here.
As you alluded to, you and Gene Cernan spent more time on the moon than anybody else and got your hands really dirty. And I've heard stories that you kind of breathed in a lot of the moon dust and got a little bit of lunar hay fever, and I just wanted to know what that was like.
Indeed, I did breathe some dust, like everybody else did. I at least reported and I think I may have been one of the only one that really noticed a significant swelling in my turbinates inside my nose. That gradually went away. It didn't bother me at all. It went away by the next morning. I didn't notice it at all. And the reason for that, I think, and I'm hesitating a little bit, the reason for that is that the individual particles of dust that you breathe in the cabin that have come off your suit haven't yet fully deactivated by absorbing oxygen and moisture and things like that. And therefore you get the sensation you're breathing gunpowder. Gunpowder is activated carbon, really, after you shoot. And and I think the same thing is happening with the lunar dust, is it's just very activated and stimulates the same kind of response. However, I know of a flight surgeon who was assigned the task to get our suits out of the spacecraft when it was on the carrier after we landed. And he went in to get these suits, and he had such a reaction to the dust on the suits that he couldn't complete that task. And so that sounds like that dust would have been fully deactivated. So I think there's more to the dust question than we understand. But I'm not going to worry about it because there are engineering solutions to keep it out of your habitat. You don't have to breathe that dust. And so, and they're relatively straightforward solutions too. So even though there's a cottage industry around studying lunar dust, I don't think we're going to have a problem with it.
Another question over here.
Hi, I'm doing my master's thesis on walking, skipping, and running in fractional gravity environments like the moon.
Yeah.
So I've seen the video of you guys singing along to Bugs Bunny about 1 million times and talking about skipping on the moon, and was wondering if you could talk about how you fell into that pattern and what it was like doing different locomotion
Okay,
styles.
my skipping was more of a cross-country ski stride. I learned cross-country skiing when I was a Fulbright student in Norway, and I found that was the most efficient way to go any significant distance. Gene Cernan and other pilots tend to like to hop, and occasionally they would skip. But I don't think that's a very efficient way of traveling. So let me suggest that as you study this, study cross-country skiing as well. And there you glide above the surface, of course, instead of on it. But you can use your toe push, and if you had a couple poles for stability, I think you could outrun the rover, as a matter of fact, because it's really very efficient. So just a suggestion to add another fourth element to your studies.
Hi, as the only scientist really to walk on the moon, it'd be interesting to hear if you were given the opportunity to send a scientific investigation today, who would you send and where to do what on the moon?
Well, if we had the capability, as I think we should, to have 4 people in a lunar lander, I would make 2 of them geologists. I'd train them to fly jets and helicopters and everything else like I did, because I think it's an important psychological aspect of the whole thing, but as well as developing new skills. But I think you need to have field geologists, and I emphasize field because there are geologists who never go into the field. And what you got to observe nature, and you have to have the experience in doing that and understanding what is important and what may not be important, but always keep an open mind that anything there could well turn out to be very important. And that's happening today in spades with our studies of lunar materials, is samples that we didn't think would turn out to be very important are just tremendously important based on new analytical techniques that we have. So I have no problem that you need the test pilots, the experienced pilots to maneuver vehicles in space, and I'm not a big advocate of autonomous landing yet, but I'm going to have to be to get to Mars. You don't have the communication links landing on Mars that we had to land on the moon, and that's going to take a whole different philosophical approach, I think, to how you operate, how you actually land a vehicle on Mars for a crewed mission. So I would have a couple pilots, I would have a couple geologists, and I'd have everybody cross-trained so they could do whichever task needed to be done. And that's basically what we did for Apollo, and I think it's a good approach.
And Jack, a couple of astronomers to go down there too to
Well,
lay out some low-frequency telescopes.
Well, now that's a different task. I think that's a whole new mission that needs to be done. Jack has been trying to brief me on low-frequency astronomy from the far side of the moon for many decades now, and I think he's onto something very, very important if you really want to understand the dawn of the universe, right? Communicate with God, so to speak.
I mentioned to a couple friends that we would have the opportunity to hear from you today, and got a range of responses. One of them was, "Oh, really? Ask him if he just preferred to stay there." And another was on the other side saying, "What was it like working with a green screen in the Arizona desert?" So my question is, how do you deal with the naysayers? Those, and many of them inside and also outside of America, who say, "Oh, no one's ever been on the moon."
There aren't very many, and I just ignore them, frankly.
Let's see. I think we've got time for one more question.
Let me add just one thing. Charlie Duke has a good response that I've heard, and that is, if we fake the mission once, why do we do it 9 times? That's a good question. Next.
So I believe one of the biggest challenges facing humanity today is anthropomorphic climate change. I've read some of your previous statements about the subject, and I'm just wondering if your thinking has evolved in that area to start accepting the actual seriousness of this issue.
Well, we probably ought to stick with space stuff, because I don't think we need to get into that. I view those issues and all issues from as pure a scientific point of view as I possibly can, and that's where my opinions come from.
I didn't want to ignore you all over here. I know there's a couple of hands, so who wants to?
So you were on the moon longer than I realized, and I wondered if you could tell us what it was like when it went from day to night there.
Well, we only saw the change from day to night when we were in orbit, because we were on the surface of the moon only 3 days, and the sun, it takes 13 days for the sun to go across. And so we didn't see night. I was in deep shadow a couple times, and it's amazing how much you can see in deep shadow because you're getting reflections not only from the surface itself, but from your suit. You can direct sunlight into these shadows. But in orbit, we did several times turn out all the spacecraft lights, dark adapt, and look out into space, as well as watch sunrises. And it's a lot like watching an eclipse, near the end of an eclipse. You start to see these streamers of zodiacal light coming off the sun. Each of these streamers has a spike of bright light just before sunrise. And it's really a remarkable experience. Now some of the glow we saw, I think, is because of this transient atmosphere that I mentioned. That, for example, sodium is a component of that transient atmosphere, and I think some of the glow we're seeing is not dust, levitated dust, but is the effect of that transient atmosphere at sunrise when you have a very long path link towards the sun right at the horizon. But I can't prove that yet, but I think that's my hypothesis, okay?
Well, let's thank Dr. Schmitt once again for a wonderful presentation this evening.
Thank you. Appreciate it. Great to be with you.
And we've got a couple of different doorways to go out. We've got a VIP door over here to reception, and other folks can go out through this door over here. And so a little bit of guidance from that, and a little appropriate music to help guide us out.
Hey kids,
Thanks
how you
everybody.
Doing? Huh? How you doing? Great to see you. Hey, how are you? See you. How's it going? Pleasure. Hey. Good to see you all. Thank you. Thanks for coming. Appreciate it. Yeah. Hey, how are you?
Tito's wife, Mary.
Oh, Mary, how are you?
Nice to
Yeah.
meet you.